If equation has more than one radical, you isolate one of the radicals. I usually try to put it on the left side, and then you multiply it by a power of the root. So, in this case, first thing we want to isolate this radical. Move it to the other side. Move the 5 to the other side. Now we're going to square both sides. And when we square both sides, square root of p squared is p. 4 squared is 16. There's your solution. And then they're going to check it to make sure it's okay. Remember, we have to do domain checks on radicals, because now we're dealing with equations, not just expressions. Okay, in this case, we want to move the 3 over to the other side to isolate the radical. Square both sides, and you get x equals 25. You can check this. 5 minus 3 is 2. It checks. This one looks a little scarier. Still, we've got to isolate this radical, so we take the 2 over, and we get 4. Now, because this is a cube root, we're going to cube both sides. Well, this cubed gives you the radicand. That cubed gives you 64. We'll take the 1 over to the other side, and we get w equals 65. Now we have to check it to see if it's true. On this problem, you need to get the 9 and the 7 over here together, so you've got the radical isolated. Now I'm going to take both sides to the 4th power. That'll give me x plus 3. In this case, it'll give me positive 16. We take the 3 over, and then we check it to see if it works. In this case, we got a falsehood when we put that 13 in there, so there is no solution on this problem. Okay, for this problem, to the 1/4, so we convert it to radical notation, 4th root of x minus 1. Take the 6 over to the other side, so we get -3. Then we take the 4th power on both sides. Well, that gives me this, the radicand. And over here, -3 to the 4th is 81. I take the 1 over to the other side, and I get 82 equals x. We do a check on it. In this case, it does not prove to be true because we get opposite signs on our answers. And I checked it from this step right here. Now we've got a variable on here as well as numbers. So let's get the variable on the other side so we've got this radical isolated. Now, I could divide both sides by 2, but that would make this thing terribly complicated. So I'm going to leave this 2 here when I square both sides. Well, I have to square the 2, which is 4, and then when I square this radical, it becomes a 4y minus 3, so I get 4 times 4y minus 3. This side I have to FOIL. First term squared plus 2 times first term times last term, and last term squared, using the shortcut. Now I combine like terms. So I take the 16y over here, I take the -12 over to the other side, and end up with this quadratic. We got to factor it. It factors into these two terms. Now we're going to use the zero products, which creates two problems out of these. This or that. And then, so we get these two solutions. Well, we have to test both solutions now that we have equations. Here's the check for the 21, and it comes out false. The check for the 1 works out true. So then our answer is only x equals 1, or y equals 1 in this case. What if you've got multiple radicals? Well, first you isolate it so there's just one radical on one side and anything else is on the other side. Since this is a cube root, we're going to cube both sides. That'll give us this. This will give us that radicand. And now it's a matter of combining like terms and solving the equation. Now, so far, with radicals on both sides, it hasn't been any different. But if there are additional terms out here besides just the two radicals, then it gets a little more complicated. By the way, here's the check for this one. Okay, notice on this one, I've got a radical, and a number. First thing I've got to do is isolate one radical. So I've got this radical on the left, and I've got everything else on the right. I'm going to square both sides. Now, I'm not just squaring this radical individually, and right here's the biggest mistake that students make on this kind of problem, is they try to just square this individually and square that individually, but it won't work that way. You have to FOIL this binomial. This one is easy. It's just the term, the 3m minus 1. They're just bringing that down. It hasn't disappeared. Okay, when you FOIL this, you get the first term plus 2 times the first term times the last term, and the last term squared. So this gives you, simplifies to m plus 4 when you square it. This one, you just got that stuff, and then the 1. Now, we finally brought this down. We combine like terms that we can. Okay, now I still have a radical. Now I could square both sides right now, but since 2 will go into both of these terms, I'm going to divide both sides by 2. So that just simplifies it a little bit more. Now we'll go to the next page, take where we were. I'm going to have to square both sides a second time on this problem. Okay, when you've got multiple radicals plus additional things, you're actually going to have to square both sides twice. So this one we square, and that one we square. We have to FOIL this, getting those terms. This one, just m plus 4. Now we take the m and the 4 to the other side, combining like terms, and we get this. We can factor in m out of both of these, giving that. So that gives us values of m equals 0 and m equals positive 5. And we have to check both of those. Remember, when you have something like this, when you have 2 radicals plus additional stuff, you're going to end up squaring both sides twice. In this case, one answer worked and one answer did not work. Once again, in addition to the two radicals, we've got an extra term, so we're going to end up squaring this one twice. There we do it the first time. This will just be 5x plus 4. This we have to FOIL. Here's the FOIL of it. First term squared, 2 times first times last, and last term squared. Simplifies to that. And this one, of course, just is the radicand. Now we combine terms as much as we can. We take the 5x over here, the -2 over here, so we get a single radical again by itself. They did that in 2 steps. I can divide both sides by 2. Now I square both sides again, leaving me that, which is a simple equation to solve, and I get 12/5. We can check that, and it does check to be true. And that's where we're going to stop for tonight. Tonight, we're going to work on complex numbers. Now, if you looked at the video that I emailed all of you, or the first video that was in the link that I told you about, I did talk about complex numbers some at that point. So we're going to talk about first the definition of imaginary numbers. Imaginary numbers, by definition, are the square root of 1. These are numbers we can't graph. I've mentioned that in class previously, but yet they represent mathematical locations on graphs that are above or below the axis. Now, if this is true, then it follows that I square equals -1. Here's the list of perfect squares. With these perfect squares, if you notice down here, if I squared is -1, then the square root of -1 is I. Just like if 25 squared is 625, the square root of 625 is 25. They follow exactly in the same pattern. Here are some examples. If we have the square root of -64, we break that down into -1 times 64. The -1 will extract as an I, and the 64 will extract as an 8. So your answer would be 8i. In this case, -50. Well, we change that to -1 times 50. We extract the -1 as an I, and then we have to find the square root of 50, which in this case breaks down into 25 times 2, and 25 is a perfect square, so we can extract that 5, and we've got the I that we bring down, so the answer then is 5i times the square root of 2. In this problem, we've got a negative on the outside, which will just carry through for us until the very end. You can see it here. We changed it from just a negative to a -1. Okay, the square root of -4 becomes -1 times -4. The 4 extracts to a 2. The -1 extracts to an I. So we get the original -1 times 2i, which was the radical, or a -2i. Square root of -29, we don't have a perfect square this time. We extract the -1 and get an I, and then we just have to leave the square root of 29. So this would be your final answer. For examples, first we're going to extract the -1 for the I, and then the square root of 81 is 9. We extract the -1 for the I, and then we break 20 down into 4 times 5. The square root of 4 is 2, and it leaves radical 5. Here we carry down the negative. We take a -1, which is the I. Square root of 36 is 6, and here is the negative we brought down. In the case of -7, we extract the I from the -1, and we bring down the square root of 7. We've got a fractional one here. Of course, you can't leave a radical in the denominator, but this one's nice because it becomes a perfect square down here. In this case, the -1 becomes I, and the square root of 100 is 10. The -1 becomes I, and the square root of 25 is 5. Then we do a simple reducing that fraction. The i's cancel. I divided by I is just 1, and 10 divided by 5 is 2. Here we have the product of 2. This gives us an I. That gives us an I, a 5, and a 3. So this simplifies to 5i times 3i, which gives us 15i squared. But by definition, I square, the definition of I squared is -1, so we have to replace that. And our final answer then is -15. Here we've got an I, there we've got an I. If we multiply these two together, we got a 25. Or a square root of 5 squared. In either rate, whether you call this square root of 25 or whether you call it square root of 5 squared, it extracts to a 5, and your final answer is -5. In this example, we can extract a 6i in the numerator, a 3i in the denominator, do simple reducing of the fraction, and we get 2 for the answer. Over here, we've got 4i and 7i, gives us 28i squared. We replace the I squared with -1. And by the way, showing that I squared becomes a -1 is a critical step for getting partial points on any test. And then the final answer is -28. We can extract the I in both locations, multiply the square root of 2 times square root of 2. You could have this as square root of 2 quantity squared. And then the i's give you I squared. Replace the I squared with a -1, extract that 4, and you get -2. Any questions on this type of problem to this point? I don't see any hands going up, so we'll keep on going. Now we're going to have the powers of I. I'll let you look at this chart just for a moment and see if you can find some consistency in it. What are all the answers? Either positive or -1, or positive or -I. Now, let's see how we get these answers. Here's our first example. If we had I to the 13th, what we have to do to that is we've got to come up with a set of I squares, which we have a conversion factor of -1. Well, 13 is an odd power, so we break it down to its biggest even power times I to the first. or in this case, I to the 12th times I to the 1st. Now, the I to the 12th becomes I to the 2nd to the 6th power. And then we just bring this I down. We replace I to the 2nd with -1. And then -1 to the 6th power, being an even power, gives me a +1. And I bring down the I. So my final answer on this problem is just positive hidden 1 I. Okay, in this case, 18 becomes I squared to the 9th. That's an even power, so I don't have to have the extra I to the 1st out to the side. We replace the I squared with -1. Now, I squared, or -1 to the 9th power, an odd power, gives me a negative answer. We've got an odd power of I. So we have to break it down into the highest even power times I to the 1st. Now, 106 divided by 2 is 53. So this becomes I to the 2nd to the 53rd power. We just bring this one down. We replace the I to the 2nd. A -1 to an odd power, a -1 to an odd power gives you -1, and we bring down the I. So in this case, our answer is -1I, or just simply -I. 32, it's an even power to start with. So we just take 32 and divide it by 2 to get 16. Replace this with a -1. -1 to an even power is +1. Are you seeing the pattern in all of these? If you are, hopefully nod your head, where you find out how many I squareds you can have in it, and then convert the I square to get your answer. Now, a complex number. Complex numbers come in the form a plus bi, where a is just a number, b is just a number, and then you've got I. This is a real number. The a and the b are. But the composite of this is what we call an imaginary or complex number. This is the standard form. Anytime you give it from this point forward the answer to a complex number, you need to give it into this form right here, where you've got some number. Now, this could be a 0, in which case it wouldn't show up. If that's a 0, there's no I, so you don't have to worry about it. This is a pair of complex conjugates, and we use those to eliminate denominators, just like we did the conjugates to eliminate denominators with square roots. If we go to number theory, the set of complex numbers includes the counting numbers, the whole numbers, the integers, the positives, negatives, the fractions and the decimals and the repeatings, then the values like pi, e, square root of 2, actually square root of any prime number. And then the imaginaries are the ones beyond that. And we call the entire set the complex simply because they contain a real component. Now, this is kind of simple. Identify the real and imaginary parts. -8's the real part, 2i is the imaginary part. What about this one? Well, that's just the real part, because The absence of an imaginary means that the coefficient is a 0. This one, we're missing the real part, so it has to be 0. Okay, when we get ready to add and subtract these, it's very simple, kind of like we did with variables right at the beginning. Real numbers with real numbers, imaginary numbers with imaginary numbers. So in this case, we would add the 1 and the -3 together. And then we would also add the -5i and the +7i together. Now, I don't require you to show this step. This is just kind of what you're thinking. I'm going to add the 1 and the 3 and the 5 and the 7. Ending up with -2 plus 2i would be your final answer on this one. When we do subtraction, just like we had to before, we have to watch out for a minus in the middle, because that minus will change the sign of both of these in the parentheses that follows. So we've got 1/4, okay, -1/4 minus 1/2, and then the 3/5 and minus a negative gives you a positive on this, and then they just undistributed this I out of the 2 I sets. So anyway, you got to add these, and you got to play the common denominator game. You've got to play the common denominator game here as well. So that's your common denominators. And then, so we end up with, out of the real numbers, we end up with -3/4, and out of the imaginaries, we end up with 7/10 I. Here, we don't start off in the imaginary form, but we've got negative square roots, which will cause us to have imaginary numbers. Okay, this is going to be -1 times 4 times 2, and this will be -1 times 9 times 2. Well, the 4 that I said was in here extracts, as well as the -1. The 9 and the -1 both extract here. So we have a common term here that we can continue to add these to. So we got 2 of these, 3 of those, a total of 5i radical 2. Now we're multiplying a pair of binomials. You can either do multiple distribution, or you can FOIL it if you choose. I don't care which way you do it. The demonstration here shows multiple distribution, where we take the first term times both, then we take the last term times both. That gives us this set of terms. 10 times 2, 10 times 3i, -5i times 2, -5 times 3i. And then we simplify this. 20, 30i, -10i, and in this case, the i's give you an I square and a -15. The next step we have to do is we have to convert the I square into -1. Well, what that'll do is that'll totally get rid of any i's right here. So then we can take this 20 and this converted I square and add those, and that would be our final answer. if we look closely at these two values, we have a conjugate pair. We have the same first term and the same last term. Because that's the case, we can use this rule C off of my handout, and our answer will become this form right here. So we're going to take the first term and square it right here. And then we're going to take the last term and square it with a minus in the middle. 1.2 squared is 1.44. 0.5i squared is 0.25i squared. Now we convert the I squared to -1, giving us this value, which we can combine, and ultimately our answer is just a simple 1.69. We don't have to show the plus 0i. Division and simplification. Well, if you recall from when we did square roots, if we had something like this, where we had a binomial on the denominator, we had to multiply the numerator and denominator by the conjugate. That works the same way with imaginary numbers or complex numbers. So we multiply the numerator and denominator by the conjugate of 5 plus 2i. The numerator, we just have to FOIL. The denominator, we can use that a squared minus b squared trick. Here's the first term squared, last term squared, minus in the middle. Here are the terms when you FOIL or distribute the numerator. We'll go ahead and simplify those a little bit. We've got an I squared that'll have to be converted there, and one that'll have to be converted here. So we're going to do that on these. Replace them with a -1, resulting in these values. Now we can combine the 20 and the -6. We can combine the 25 and 4. This last step, this term has a common denominator of 29. Well, to use that silly word I made up, uncommon denominator allies, I've broken this down into 14 over 29 minus 23 over 29i. This now is in what we call standard form. A plus, or minus in this case, bi. That is a necessity. Forgetting to convert this to the a plus bi format is a 1-point deduction on a test problem. What about this one? What if we want to simplify this? Well, first we've got to extract the I in here. And then this becomes 9 times 2, and the 9 extracts to this 3. So we do have a common 3 term in all of these, but first we could put it, which they factored out. We're going to cancel this 3 and this 9. So now we've got this value, but this is not in standard form. So we have to make it 2/3 plus square root of I over 3. Now, when you write an answer like this, make sure it's very obvious that that I is not underneath that radical. We'll go to chapter 7.